Okay, let's see what. So a roughly even split between A and C, with a few of you thinking maybe there's no force at all. Well, we know that if we've got current moving in this loop, that's like moving charge in the field due to this loop. Do we remember how that right-hand rule works? So let's see. We'll first use the right-hand rule to determine the direction of the magnetic field. Let's do that. So I grab the current. Now, current is going like that through both loops. Okay? Grab the current with my thumb pointing in the direction of the current. My fingers are wrapping in the direction of the magnetic field line. So out here, the field is pointing like, the field due to this one is pointing like that. Okay. So now we use the second right-hand rule, right? Or is it the first one? I forget. The one telling us the force on a moving charge. Oh, go away. Know who that was. So we have now magnetic field that is pointing in this direction, we said. Current like that, my palm pushes in the direction of the force. So from that point of view, using that right-hand rule and the direction of the magnetic field, we get that the two loops attract. And that is the correct answer, A. Anyone puzzled by that still? Yeah, maybe, but let's move on. So yes, let's talk about Helmholtz coils. They're often used in different demonstrations and even laboratory measurements requiring a magnetic field, because you can create a fairly uniform magnetic field in the nice open region in between the coils. And that gives you a place to put your little experiment, whatever it is. Suppose you want to measure the magnetic effect on some protein. You could do that. Okay? And you can change the amount of magnetic field that you have just by cranking up the current or having more and more coils. So you can design the magnetic field to be just what you want. It's a nice physical arrangement anyway for doing that. Now, let's do this experiment. We're going to turn on. Okay, we're going to get rid of this. Okay. This thing should have warmed up by now. And if I go to the next screen, it's nice and dark. What do we see down here? You see this loop of light. It's actually coming from electrons, which are being boiled off a filament here and shot at some small energy, and they're going around in a circle around the magnetic field lines created by this Helmholtz coils. And if I dial the field stronger, the loop gets smaller. You can see a beautiful circle of light there where the electrons are ionizing the gas. The gas gives off a nice glow. If I turn down the current, the magnetic field gets weaker and the circle gets bigger. Okay. So that's pretty interesting. Let's see if we can use, again, the right-hand rule to figure out the direction of the magnetic field. Okay, so we know that we have electrons. Electrons are negatively charged, right? And they're going in this direction. So therefore, which is the direction of the force on the charges inside the tube? So let's start from the force. The force has to be directed toward the center of the circle always, right? To get something to move in a circle, there's a force directed toward the center of the circle. So let's just talk about the force at the top. So electrons going that direction at the top have a force downward somehow. Now that's due to magnetic field. Now your thumb goes in the direction of the current. The electrons are going like that, but that means the current is going in the other direction. So right hand thumb goes in the direction of the current. force is down, that means our magnetic field lines are going in at that point. So these two coils are arranged. We sent the current in a certain direction such that electrons get bent in that direction. Now, what does that mean? Let's use the right-hand rule again to try to figure out the direction of the current. Well, if the magnetic field lines are in, that means they're in over here. That means that the current must be going in this direction by the right-hand rule. Again, if I grab the coil like so, my thumb is in the direction of the current, my fingers are going in the direction for the field that we figured out. Now we could have started with the other thing. I could have told you, well, the current is going in that direction, so we could take the right-hand rules and figure out whether or not we had positively or negatively charged particles inside that tube, for example. So that's how you use both of those right-hand rules in the same setup. Just turn all that down. So that's how Helmholtz coils work. But why stop with just two? No reason. If we line up a whole bunch of coils wound like this, so that current is coming out on the top here and going back in on the bottom. So this is a slice through a solenoid, and a solenoid could be as simple as, for example, this little ring here, which has a wire wound on it. If I send a current through this wire, then it creates a magnetic field which points like that through the solenoid. It gives a very uniform field in the interior, and that can be useful for various experiments or whatever you want to do with it. And the magnetic field strength that you get is proportional to the number of turns per unit length. In other words, if you have, so you just count the number of windings that you have of this current and divide by the length, the field inside is proportional to that, and it's also proportional to the current in each of the windings. So you can get a stronger magnetic field just by winding more wires. And ultimately, we're going to get to this solenoid over here, which has thousands of windings of very fine wire on it. And we'll see why we do that shortly. But let's do another clicker question. Suppose we have a solenoid of length 0.5 meters, and it has 100 turns. How does its magnetic field at the center compare with that of a 1.5 meter long solenoid with 300 turns? So this should be a quick question. I'm going to take away a little time. Discuss, think about it. Remember, the field goes like the number of turns per unit length.